We just finished working with polar coordinates, and now we're going to transition into complex numbers on a complex plane. And we will also convert from complex numbers to polar coordinates. A complex number plane looks like an XY system, except instead of X and Y, you have the real axis and the imaginary axis, if you see the image to the right on the bottom of the screen. Complex numbers are written in the form a plus bi, where a is the real number component and b is the imaginary number component. The real axis is horizontal, and that represents the real component, and the imaginary axis is the vertical axis, which represents the imaginary part. And the real and the imaginary axis together make the complex plane. You can write your complex number as an ordered pair, where A is the real part and B is the imaginary part. And you graph it just like you would an XY ordered pair. Notice that the first letter is A, which is like the first letter X on the coordinate plane with rectangular coordinates, and B is the second letter, which corresponds to Y in the rectangular coordinates. And so they match up in the same order and the same axes. I've written 4 ordered pairs for you. These represent the complex numbers 2 plus I, 2 minus I, -2 plus I, and -2 minus I. And each of these would be located in a different quadrant in the complex plane. 2, 1 would obviously be in the first, 2, -1 would be in the fourth, -2, 1 would be in the second, and -2, -1 would be in the third. The point that we have here in the complex plane AB has a real number A and an imaginary number B, and we can call this point Z. Notice that this is a right triangle that I've drawn that has one side length A and another side length B, and then the distance between that point AB and the origin, which we've called Z, can then be found using the Pythagorean theorem. We call the absolute value of Z the modulus, and it's the magnitude of Z, which is the length of a vector, and we're going to get into vectors in a couple of sections. The complex number Z equals A plus BI is in the rectangular form because A and B are coordinates in a point AB in the rectangular coordinate system, but it's formed in the complex plane rather than in the Cartesian coordinate plane where you're dealing with just real numbers. A and B can be written in a coordinate AB. That point is in the rectangular coordinate system, but it's in the complex plane. We can transform this into polar form, knowing that A, which is the x component, is r cosine theta, and B, which is the y component, is r sine theta. And just like in the rectangular coordinate system where x squared plus y squared equals r squared, a squared plus b squared equals r squared in the complex plane. Remember that the tangent of theta is equal to the opposite over the adjacent, or b over a, where a is not equal to 0. And then we can say that z is equal to r cosine theta plus r sine theta I. And if we factor out an r, z is the same thing as r times cosine theta plus I sine theta. Here is an image that represents this information. So in the complex plane, we have this point Z. Z is the point AB, where A is the real number and B is the imaginary number. And A can be rewritten as r cosine theta, and B can be rewritten as r sine theta. Using this triangle here, remember this is side length A and side length B. The tangent of theta is B over A. And we have, if you were to do, let's say, the sine of theta that's b over r, or r sine theta equals b, and the cosine theta equals a over r, or r cosine theta equals a. That's where those values are coming from. Theta, remember, as we're going in circles, we have coterminal angles. Theta can be any choice you want to be, but we'll typically stick to the interval from 0 to 2 pi. So your values could be larger than 2 pi or less than 0, but we're going to stick to writing our values on the intervals from 0 to 2 pi or 0 to 360. A few things to note. You might see z equal to r cis theta, where cis stands for cosine I sine. I will not use that notation, but I just want you to know it. If you're Googling or trying to see something on YouTube that's different, it's representing cosine I sine. In addition, we have Euler's formula. And yes, I know it looks like Euler, but it's pronounced Euler, O-I-L-E-R. That says that e to the I theta is the same thing as cosine theta plus I sine theta. And so you might see some complex number that's written z equals to, let's say, cosine pi over 3 plus I sine pi over 3. We can write that as 2, and then cosine I sine is e to the I, and then our theta was pi over 3. Or we can write that as 2e to the pi over 3i. Those are the same thing, they're equivalent. Converting from rectangular form to polar form, first you want to find r, and r is found by taking the square root of a squared plus b squared. And then you want to find theta by taking the inverse tangent of b over a. And remember, you want to keep your angle between 0 and 2 pi. To convert from polar form to rectangular form, you first evaluate the trigonometric function, and then you distribute your r value. So for the above function, z equals 2 cosine pi over 3 plus I sine pi over 3, you would find what cosine of pi over 3 is from the unit circle and what sine of pi over 3 is from the unit circle. And then you would distribute the two, and then you would have your answer in rectangular form.